Hello and welcome to my rework of the second video I'm doing on multiple valued logic. I'll be presenting an algebra system which is not mine. This is the reference for the algebra system, a many valued algebra for switching systems by these authors. IEEE Transactions on Computers, volume C19, 1970. So it's their algebra. I'll be presenting an algebraic method of minimization and minimization by Karnaugh Maps. Right. First we have the functions of the algebra. Here we have the minimum of and the maximum of functions. The minimum of just takes the minimum value of whatever on its inputs A and B. The maximum of just takes the maximum of whatever it's on its inputs A and B. So there we go. Unary operators, these are one input, unary meaning one input. Unary operators, there's A, 0, 1, 2. A plus adds 1 to A modulo 3, so 1, 2, 0. A minus takes 1 away from A modulo 3, so 2, 0, 1. These are two valid unary operators, A1 and A2. They are a 1. A1 is a 1 if A is a 0 and 0 otherwise. A2 is a 2 if A is 0 and 0 otherwise. A plus 1 and A plus 2, well, these functions are derived by first applying A plus and then A1. So A plus is a 0 at 2. So yeah, A plus 1 is a 1 there and 0 everywhere else. And then similarly, A plus 2 is a 2 when A plus is a 0 and 0 everywhere else. A minus and A minus 2 is a similar thing. When A minus is 0, A minus 1 is a 1 and 0 everywhere else. A minus 2 is a 2 when A minus is 0 and 0 everywhere else. Here I have some ternary algebraic rules. Firstly, A1 max A2 equals A2. A plus 1 max A plus 2 equals A plus 2. A minus 1 max A minus 2 equals A minus 2. A1 min 1 equals A1. A2 min 1 equals A1. A min 2 equals A. A max A equals A. A1 max A plus 1 max A minus 1 equals 1. A squared A2 max A plus 2 max A minus 2 equals 2. So A max A plus max A minus equals 2. A minus 1 max A plus 2 equals A. A1 max A minus 2 equals A plus. A plus 1 max A2 equals A minus. And lastly, A min 1 max A equals A. Note that since I'm using the minimum of function, A1 min B1 equals A2 min B1, which equals A1 min B2. That's basically because the minimum value of 2 and 1 is 1. So I can quite happily change A or B to a 2 without affecting the function. And similarly, factorisation, A min B max A min C equals A min B max C. Similar to Boolean algebra factorisation. Now we're going to have a look at the ternary Karnaugh maps. I have two Karnaugh maps, F1 and F2. F1 deals with the zeros and ones, and F1 deals with zeros and ones, and F2 deals with zeros and twos. Now we can see here that this row, this column, is denoted by A1. This column is A minus 1, and this column is A plus 1. This row is B1, this row is B minus 1, this row is B plus 1. I've written not A minus and not A plus, not B, not B minus, not B plus. It's not B only in the sense that if this column is not A, then these two columns must be A, and henceforth that goes for all the others. If this A minus, this is not A minus, then A minus is these two columns here. A plus, not A plus. A plus is these two columns here. B, not B, these two rows. B minus, these two rows. B plus, these two rows. Now you can loop in groups of 1, 2, 3, 4, 6 or 9. Here for Karnaugh map F2, we have, you group in single coordinates or groups of 3 or group of 9 if you're looping the whole Karnaugh map. But so a coordinate here would be A plus 2, B2. If you want to use an A, you can only do that if the corresponding coordinate in Karnaugh map F1 is an A. So if I had 2 there, I'd need to be, these would need to be 1s here. So I can loop an A there to give an A there, otherwise I'd have to use A plus 2. And similar for B. Yeah. Right, here we have the Karnaugh map coding. This is F, 0, 1, 2 and don't care state X. F2, Karnaugh map F2 and Karnaugh map F1. So if F is a 0, F2 is 0 and F1 is 0. If F is 1, F2 is 0 and F1 is 1. If F is 2, F2 is a 2 and F1 is a redundant state. And if F is a don't care state, both F1 and F2 are redundant states. The value of R in F1 can be a 0 or 1. The value of R in F2 can be a 0 or a 2. So here we have an example 1, a ternary function with A and B in the inputs. There's F1 and F2. I've written in the terms here of the min terms of the expression. So a 1 here would be A minus 1 min B minus 1. A 1 there would be A plus 1 min B minus 1. A 1 there would be A minus 1 min B plus 1. And a 2 would be A plus 2 min B plus 2. Right, so I'm going to go through the algebraic minimization. These are the said min terms that I've just shown you, and this is a redundant term. This is because this term produces a 2 and this term produces a 1 for the same coordinate on the Karnaugh map, and a 2 maximised with a 1 is a 2, so I can quite happily introduce that into the expression if I wish to use it. Sometimes it's advantageous to use these redundant terms, sometimes not. So anyway, in this case I haven't used that. I've just taken that term there and changed the plus 1 to plus 2, that term there and changed the plus 1 to plus 2 and put that term there. So what can I do? Well, I can factorise the A minus 1 out here and collect the B terms, and factorise the A plus 2 here and collect the B terms. So B minus 1 or max B plus 2 equals B. Similar thing here. So on this line I factorise the B. So you're left with A minus 1 max B plus 2 and that equals A. So you've got the function of F equals A and B. On the Karnaugh maps, well, I haven't shown you it yet, but F equals F1 max F2 and F1 equals 1 and 1 min A min B and F2 equals A min B. So that total, that equals A min B. This is the Karnaugh map. So you can see that F1 we have here, we've looped a group of 4, and this is not A is this, so this must be A, not B is there, so this must be B, so this is A and B. But A and B would normally produce a 2, and Karnaugh map F1 only deals with 0s and 1s, so I have to put a 1 in front of the A min B to make it all 1s. Karnaugh map F2, well, there's only one loop there, just 2, and that equals A and B, because I have A there and B there, A there and B there, so I don't need to use the A plus 2, B minus 2, I can use A and B, so that's A and B. So F2 equals A min B. This is example 2 of another function. F2 and F1 are as before, as the coding, and I've included the terms here. So there's a 1 here which is A minus 1 min B1, a 2 there which is A plus 2 min B2, a 1 there which is A minus 1 min B1, a 1 there which is A1 min B plus 1, and a 2 there which is A minus 2 min B plus 2. Now what I've done here, I'll show you the Karnaugh map first. Right. First of all, look at Karnaugh map F1. I've looped the redundant terms there with these 1s to give a whole looped a whole column which is A minus 1, and I've got a loop of 2 here which is A plus and B plus 1, and I've got a loop to 2 here which is A B1. Now on this loop, and Karnaugh map F2, I've looped a 2 here which is A B2, and because it would normally be A plus 2 and B2, but because I've got an A here, I can write an A there. And similarly here in this coordinate, I've got an A plus here. I can write an A plus instead of A minus 2 because I've got an A plus in this loop here. So that would normally be A minus 2, B plus 2, but because I've done that, I've got A plus min B plus 2. So F1 is A minus 1, max A min B1, max A plus min B plus 1. And F2 is A min B2, max A plus min B plus 2. Now I'll show you Karnaugh Maps, Karnaugh Map Minimization. So F1 is this lot, F2 is this lot. So what I've done is I've factorised the B1 and the A term here to give B1 or B max B2. And I've factorised the A plus here to give B plus 1 min B plus 2. Now that equals B2 and that equals B plus 2. So I'm left with F equals A minus 1 max A min B squared max A plus min B plus 2. Here we have the algebraic minimization. Right, I've included all the terms in the table of the function here. I've also listed the redundant states, redundant terms here. That's because A plus 2 min B2 is equal to, well, A min 1 min a plus 1 min b1. That's a 2 and that's a 1, so that equals a 2, so I can include that. And the same thing here, a minus 2 min b plus 2 there, and I've got a minus 1 min b plus 1 there. So I've labelled these 1 and 2, and that's because I'm going to use all these 5 terms plus this redundant state here. So I've used that term there, that term there, I've used that term there, and that term again there, which I've changed b to a 2 instead of a 1. I've used that term there, and I've changed that b plus to a 2 from a 1. I've used that term there. So what can I do? Well, I can factorise an a minus 1 out there and collect the b terms there. Factorise a b squared there and collect the a terms there. Factorise a b plus 2 there and collect the a terms there. Now, this term equals 1, which is there. This term equals a, which is there. The term equals a plus, which is there. So a min 1, a minus 1 min 1 equals a minus 1. So there we have the results. Right, this is example 3. A different function again. We have a 1 there, which is a1 min b1. A 1 there, which is a plus 1 min b1. A 2 there, which is a2 min b minus 2. A 2 there, which is a minus 2 min b minus 2. A 2 there, which is a plus 2 min b minus 2. So I'll show you the Karnaugh map. So here in Karnaugh map F1, we've got a loop of 4 there. I can't loop in groups of 6 because I've got a 0 there. I have to do 2 loops of 2 and link them together. So this would be not a minus, this is not a minus, so this is a minus, and this is not b plus, so this must be b plus. And again, because you only deal with zeros and ones, I have to put a 1 in front of the term, because otherwise it would produce a 2. So I've got 1 min a minus min b plus. And for Karnaugh map F2, well, there's nothing I can do there. I've just looped the whole row and made it equal to b minus 2. So F1 is 1 and a minus min b plus, 1 min a minus min b plus, and F2 equals b minus 2. So here we have Karnaugh map minimization. F1 equals that, F2 equals that. It's a straight definition, no factorisation required. Here the algebraic minimization. These are the terms of the function that are from the table. I've included the don't care terms, or redundant terms should I say, here and here, from that one there, that one there, and that one there. I've labelled them that 1 and that 2 because I'm going to use these 2 redundant states and I'm going to ignore this one. So I've used that term there, that term brought on there, and take the 1, change the 1 to a 2. I've used that term there, I've used 2 here and changed that to a 2, and I've just straight copied the 2 3 terms there. So, well, I can factorise an a plus 1 here to give the b terms, an a minus 1, a1 here to give the collection b1 max b minus 2, and I can factorise a b minus 2 here and collect the a terms there. So this b1 max b minus 2 is b plus, same thing here, b plus. This equates to 2, so you got 2 min b minus 2, and what I'm going to do here is introduce a 1 in front of this term and a 1 in front of this term. That means that I can change this 1 to a 2 here, because 1 min a2 equals a1, and the 2 min b is minus 2 is b minus 2. So I can factorise the 1 and the b plus here, and that leaves me with a plus 1 max b squared, b2, and that reduces to a minus. So I've got f equals 1 min b minus min b plus max b minus 2. Right, that concludes the presentation. I hope you've enjoyed it. Well, hopefully there'll be more, so stay tuned. Cheers.